This is a significant figures and dimensional analysis lab. Let's jump right in. So, what if you were stranded on Mars and needed to feed yourself in order to survive? Or if you had to ration food for months because of a shortage? Those significant figures add up over a period of time and they become very substantial. So, you need to know the right amount to ration and you need to be precise so that you don't overuse or overbuy. You don't want it to go bad before you use it, and there's no overspending. So, scientific notation is just one small component of significant figures. But what is scientific notation? Well, it's a way to express numbers that are either too small or too large to write or calculate without becoming cumbersome. This chart that you see on this slide is just a tool to show you exactly what these exponents mean and kind of a reference tool for you. So feel free to print that out and have that in your notes. So since we're talking about scientific notation, let me just explain to you what the components of it are. So scientific notation uses significant figures that have a coefficient, right? And that coefficient is going to be anywhere between the numbers 1 and 9. 1 and 9, okay? And then you have a base, and your base is going to be 10. Your base will be 10, and then there's the exponent. Now, your exponent is a superscript, and we'll get into that a little bit later into the semester. But your superscript or your exponent is going to tell you how many times to move that decimal when you are going into or taking a value out of scientific notation. So let's just talk about the speed of light. Let's consider it. The speed of light is going to be 2.99 times 10 to the 8. Right? 2.99 times 10 to the 8. If we take that, we know that's the speed of light, and I want to take it out of scientific notation. I'm going to do that by moving this decimal over several times. How many times did I move it over? Let's see. It looks like I'm trying to land between that 2 and that 9, correct? So that between that 2 and that 9 is 8 spaces moved over. And once I move that 8 spaces over, I know that it's 8 because of that exponent. And that 2.99000000 is equal to 2.99 times 10 to the 8th. So just a little breakdown of the speed of light. So we can convert it to scientific notation, but there are rules. And like I said, the coefficient has to be greater than or equal to 1, and it has to be less than 10 with only one non-zero number to the left of the decimal. And then you have to have the appropriate significant figures to the right. So by moving the decimal 8 spaces to the left, the power of 10 is raised. And the same rule applies if we're moving to the right. The power of 10 is lowered. So we have to round numbers when it comes to significant figures. And basically the way that we're going to do that is we're going to follow this simple rule, okay? 4 or less, round on down. 5 or more, round on up. So if you have a number like 40294, this long number of milliliters, and we want 3 significant figures, we have to round it to that. And we're going to get into significant figures. But what we're talking about is we know that we want 3 numbers. So we go to our first number 4.02, and then we use that next number next to that 2 to round it to where it needs to be. And because that next number is a 9, which is 5 or more, we round up. And that's where we get that 4.03 milliliters. So knowing how and when to round your numbers properly is very important. We will always round milliliters to 2 decimal places. Just throwing that out there because we're looking at milliliters. We will touch on that many times throughout the semester. But rounding isn't only useful, but it can also help you be more precise in your answer. And let's face it, in chemistry, precision is the name of the game. Since we're talking about rounding, we need to also talk about exact numbers. So what we have here is a dozen eggs. A dozen eggs is also known as 12 eggs. That is an exact number. We know what a dozen, we know what 12 is, okay? Then we have 1 foot. We all know that 1 foot equals 12 inches. Those are known and they're given to us. Then finally, we have 1 cup. Now 1 cup equals 8 ounces. Those are known and given to us. So exact numbers are values that are known and are a complete certainty, numbers like these. They're known and given to us, and they have an infinite number of significant figures. They are common knowledge numbers. So measurements can vary according to what, who, and how someone is measuring a certain object, and are just never a given or known number. Now let's talk about our scale. So our scale, we will use this all semester in class. And if something's measured on an electronic scale as 0.581 grams, you know the 5 and 8 are correct. But the 1 is uncertain because it changed with repeated measurements of the same sample. Another student may weigh the same sample and get 0.580 or 0.582 due to the sensitivity of the scale. In measurements, 6.5 grams and 6.532 grams can both be right when we're describing the same subject or the same object, but the 6.532 is more precise given the uncertainty. So all numbers that are measured and recorded from a digital instrument should be expressed to the precision of the instrument used for that measurement. Accuracy and precision. So accuracy is based on your measured value versus your true value and how close they are to each other. And precision is based on your significant figures and when the numbers become uncertain. They both can be used to determine sources of error in an experiment. The values that are accurate and precise usually indicate that the instrument and the user are correct. Okay. There may be a problem with a measuring instrument if an answer is precise but not accurate. And then we know that if we are not accurate nor are we precise, we'll probably have an operator issue and an instrument issue. So we need to address both of those things in the effect that we are not accurate nor are we precise. So when measuring with non-digital instruments like a ruler or graduated cylinder, the last digit recording is an estimate, smallest calibration lines on the instrument. Okay, the smallest calibration line, and you see this arrow right here. That's where we're talking about. These are the calibration lines, okay? So we need to know the rules. There are rules that have to be followed when we're recording measured values or performing mathematical calculations. So the measurements result in a certain number of sig figs, and those rules are going to be listed for you on page 5 of your Sig Figs handout. So I would most certainly like you to grab those rules, know those rules, maybe make yourself some index cards, have them in your notes. All right, I'm going to give you a quick rundown about sig figs for addition and subtraction. And I also want to remind you that there is an independent video in the video library that you can find that goes into a little bit more in depth and shows some more examples for addition and subtraction in order to find sig figs. So, excuse me. The example on the left, this one right here, shows that 2200.1 is the least precise number, so it has the least number of decimal places. Now you can think of place value. If you can find yourself a place value chart, that might make a little bit more sense. Also, I really do advise you guys to check out the independent addition and subtraction sig figs video because it is very helpful. It's got multiplication and division in there, which we're going to hit on in a second also, but it's a great video. It's only about 7 minutes. It's about 7 minutes long. So the answer should have as many decimal places as the least precise number, which is going to be the lowest place value on a place value chart. So the example on the right shows that 2.7 has 1 decimal place and it is the least precise number. Therefore, the answer needs to have 1 decimal place. Now, if we're talking about multiplication and division, those rules are a little bit different. We're going to look at all the numbers. We're going to assess the number of significant figures in all parts of the problem. And then we're going to use the lowest number of sig figs as a guide to the number of sig figs in the answer. And the result is based on rounding the answer to the right significant figure. So if I look at this particular problem, what I have is the number 2.7 has the least with 2 sig figs. Now we're looking at the entire problem, not only what falls after the decimal. So therefore the answer must have two significant figures. And if you're confused about why we have two sig figs with a final answer of 0.074, there is a rules video, and we will get into that in just a few minutes. So check out the rules video for zeros, for significant figure zeros, and that should clear up any confusion. So just a quick note. If we're working with our calculators, we have graphing calculators, right? And we're going to be entering in exponents. There is a video on calculators and how to enter in exponents also in the video library. There are so many good supplemental videos in there for you guys, so please check those out, and it gives you a little clarification. Also goes point by point and shows you how to use it. So if you have 1.01 times 10 to the 7, that is a different answer than 1.01 EE7. So if your calculator gives you an answer with EE in it, you need to convert that to times 10 to the exponent, whatever that exponent might be. My point is when you see an answer that comes across on your calculator that says 1.01 EE7, that is a calculator function and not a mathematical answer. Okay. Also, the abbreviation given is EE or EXP. That is not the same as the anti-log times 10 button. We'll get into the anti-log times 10 button a little bit later into the semester. So using these buttons are likely going to help you maintain less of a chance of making an error. And if you start to see that you're seeing errors, try to take parentheses out or putting parentheses in, and see if you can't get a more steady answer that way. So real quick, what is dimensional analysis? So dimensional analysis is nothing more than saying I'm going to take something and I'm going to take it out of one measure of unit and put it into another measure of unit. You will also hear dimensional analysis referred to as conversions. For this lab, we're going to use dimensional analysis to convert simple units. And then as we get further into our class, we're going to be doing a little bit more complicated ones. So the first thing I'm going to do here is I have 2.70 liters and I want to convert it to ounces. Well, I know because I got it off of a chart or off of an internet somewhere that 2.70 liters is equivalent to 33.81 ounces. I want those liters to cancel. And so those liters cancel because they are diagonally across from each other. Now this goes back to basic math. And we do have a dimensional analysis video and does do some really cool problems in there that might explain it a little bit more. But our liters will cancel out. We have ounces left. We simply multiply the two values and we come up with 91.287 ounces. But the point is that in the original problem, which is 2.70 liters to ounces, we have three significant figures. That means our answer has to end in three significant figures, and that's a 91.3 ounces. So let's do one more. We have 12.5 ounces to liters. So we did the exact same thing, but what obviously we did was we took the ounces and we put it on the bottom this time because we want those ounces to cancel and we want to have liters left over, and they have to be diagonal from each other in order to cancel. We put those values into our calculator and we got this really long number, which we need three significant figures, remember? So we're going to go ahead and we're going to round to three significant figures, 0.370. So that 3.70 comes from the 0.3697, that 7 is higher than a 5, and so we're going to round the number right before it up, which is going to be a 0. Okay, that means that we're going to have to round the one next to it to a 7 because we're going from 369 to 370. We're rounding up 1. All right, this is just a simple conversion chart that you're given in your lab. You're going to use this conversion chart when you're solving some of your problems, and that's going to wrap our lecture. I hope that this video is handy to you should you need it while you are studying. And please don't hesitate to reach out to me via email if you have questions before it's time to turn this lab in. I need at least 24 hours to get back to you and be able to, see you and help you. All right, have a good day.